Welcome, function folks. Day 2 of Trig Identities 3.13. We are getting there now. Only a few days left to the end of Trig. Hopefully you had some success proving some stuff. Today's not a lot of new stuff. Maybe just a chance to see a couple more examples. See maybe a couple different types. This one is fairly routine, regular. So let's give it a go. Hopefully you gave it a go and you've got the proof right there in front of you. And secant squared is over here. What's the technique? Well, the technique probably is to try and write these in terms of sines and coses. That's a good idea. So I'm going to write this as 1 over cos squared theta. Not much more. Maybe there's something here. Pythagorean theorem or a cos 2 theta. I remember cos 2 theta has a cos squared in it, but let's see what's going on the left side over here and see if we can't do something. What's tan squared theta? Well, tan squared theta is sine squared theta over cos squared theta. And now I see I got a cos squared in the bottom, so that's encouraging, but maybe we should keep working on this. I've got a fraction here and a 1 there. I might be tempted to try and get a common denominator. So let's get a common denominator. The common denominator here is cos squared theta. Cos squared theta, and then I write that over the common denominator, and awesome things happen. And that one was pretty easy, actually, isn't it? Sine squared theta plus cos squared theta is equal to 1 because of the Pythagorean identity. And left side equals right side, ... the identity is proven. Identity is proven. Okay, now this was actually on purpose. This isn't a particularly spectacular identity, but it is one that's used quite a bit. So this one is actually, another version of what are called the Pythagorean identities. Right, this is one of them. The first one, and I wonder if I can put them all together here. Yeah, let's just put that down there. This is a Pythagorean identity. The one that we're really familiar with is this one. Right, that's the one that we know and love. And this is the one that we just proved. And there's actually another one. The other one is 1 plus cotan squared theta is equal to cosecant squared theta. And we could prove that. I'm not asking you to, but this is another version of the Pythagorean identity. Now, how would you remember this? Well, you could prove them, but maybe I wanted to know these, and maybe these things will be familiar. I wanted to be able to recall them. I can't remember these two. I remember this one. And how I get the other two is just divide by cos squared theta, or we'll see. And if I take this one and divide by cos squared theta, well, that's tan, that's 1, and this is secant, right? That comes automatically. It's straightforward. When I start with the one that we love, the Pythagorean identity that we know and love, it just pops out. And the other one, the one that we didn't just prove, pops right out as well if we divide by sine squared theta. Sine squared theta. Divide each term by sine squared theta. And then that's 1. Boom. Cos over sine is the reciprocal of tan, is cotan, and 1 over sine is cosecant squared theta, rather. And there's the 3 Pythagorean identities. Yep, you can add those to your sheet, the sheet that you can't use on this test, but you will keep that handy when you're studying, proving trig identities, and you'll save that sheet also for the exam, remember, because you will have a cheat sheet for the exam. All right, that's all I have to say about that. The thing that we're doing today, trig identities day 2, same expectations, no new expectations. The example here is just to do one from the textbook. 417, number 6. They're calling it an application question, but this might be pretty close to a thinking question. It says, graph the expression, this big long expression, and make a conjecture about another expression that is equivalent to this expression. What the heck do they mean? What's a conjecture? Well, first of all, a conjecture is kind of like a proof guess, a guess of an identity. A conjecture is something that we're pretty sure is going to be true, but we don't know yet. So that's a guess of an identity, is a conjecture. So we're going to put this into our graphing calculator. I think you already have a copy of it, but this is good practice, putting stuff into the graphing calculator. Right, want to graph it. So graph 1 plus, now where's tan x. We got to be careful how we graph this. Notice right now, if I put the squared in here, and it wouldn't let me put the squared where I think it is. This is just the x squared, so I've got to be careful there. And I can even be extra careful by putting brackets around the tan here, and extra careful that I know it's this bracket squared. All right, and then n bracket, so I can have the long division bar, which is a short division bar on the graphing calculators, but you can see what I'm talking about. And notice that it should be minus on the top. The plus one is on the bottom, minus on the top. Did you notice that I made that error? You did, and you were screaming for me to make the correction. Yeah, I hear you. I heard you. X and then squared. Oh, just this bracket squared. And then an n bracket, and make sure our brackets are all lined up. That one's on the x, that one's on the tan, that one goes with the opening brackets, and then we've got it. So a nice trig window setting would be just zoom 7 for trig, and then what does it look like? It looks like a trig graph. It doesn't look anything crazy like tans. And notice here, for my scale, each tick is worth 1. I'll go back and check it here, but each tick in the direction of y is worth 1. Go back to the graph. So this has an amplitude of 1. It kind of looks like a cos graph, but it's 2 cos graphs by the time I get out to 2 pi. Two cos graphs by the time I get out to 2 pi. Well, that's just a horizontal squish, right? So it kind of looks like maybe cos 2x, right, with just a period change. And so the conjecture would be, well, let's try cos 2x. Let's put in cos 2x and see graph. And notice it doesn't look like anything's going on. That's because it's going straight in the background, right? It's exactly the same thing. I can emphasize this by changing this to a bold graph. You see, I just used my cursor keys and got back there, make that bold. There's the original. It's going to graph it again. That's this one, this crazy formula. And then the second one is the cos 2x, and look at it, it's right on top. Is this a proof that this expression is equal to this expression? No, it could just look like it. So even though the graphing calculator made us think that maybe, just maybe, that is an identity. Is this an identity? Well, and notice that's all the stuff you got there. Maybe it is, right? It looks like, it appears that 1 minus tan squared x over 1 plus tan squared x is equal to cos 2x. Is this a proof? No, not yet, but maybe we can get to it. Oh, maybe we can get to it. So the left side is this thing. And the right side is this thing. And we need to know some formulas, right? Cos 2x, well, let's see if we can. We know 3 of them, right? One of them is cos minus sin, right? Minus cos minus sin. There's a couple other ones, but we'll write that one down for now and hope for the best. But did you notice? Did you notice? Huh. 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 maybe there's a method to Restall's madness, right? This thing is equal to secant squared theta. Say, well, I thought your strategy was to write everything in terms of sines and coses. And my response would be, yeah, that's true, and I could probably prove this, but I don't want to be here all day. And in fact, if I can take a shortcut, and this takes some experience to do this. I'm going to take a shortcut. This looks better. This looks better. And what am I going to do now? Well, I know that this is 1 over cosecant, or 1 over cosine theta, rather. 1 over cosine squared theta. But if I put in 1 over cosine squared theta there, it would be a fraction over fraction. That's no fun. I'm going to write it this way. All right, this thing divided by this thing. And in fact, here, if I want to save a step, and I'm going to save a step, if I write it as a divide here, this is 1 divided by cos squared x, right? Well, now what do I got? Well, how do I deal with fractions when I'm dividing? Well, I can invert and multiply. I can invert and multiply, and now I'm having a peak back there. Notice that right now, if I were to multiply through this bracket, 1 times cos squared theta, I'd have that term. Is it possible that I could get sine squared theta out of this? Well, now let's write tan in terms of sines and coses. This is sine squared x and cos squared x. I multiply through, and geez, I got it. I got cos squared x, and then the cos squared will cancel that cos squared x. Now I'm left with, a minus. Right there in between, minus sine squared x, and the left side equals the right side. And the conjecture, the identity guess, is proven. And there's a couple like this from the textbook, and you'll get a chance to do this. This is last day stuff, and hopefully there's only 4. Hopefully you got those tried, and there's a bunch more from the same exercise, but maybe some different ones. Maybe a little bit harder, maybe a little bit easier. And these are like the conjecture ones, I believe. And I'd like you to try those. There's another FAQ for you there. And good luck with the trig identities. Day 2. Keep at it. Be patient.